With our brief introduction to vectors and matrices, we'll now look at how we can use these tools to model linear systems. We'll start by discussing linear combinations. So let's start off with the definition. A linear combination of the vectors v1, v2 through vk in Rn is any sum of the following form. So here the ci's are scalars, and we're looking at any sum of the vi's. Let's make this a little bit more concrete by looking at example in R3. So for example, the vector -1, 4, -5 is a linear combination of the following two vectors. Now, I don't expect you to be able to see this directly, but we can verify it if I give you the scalars. In this case, we'll take 2 times the first vector and -1 times the second vector. And you can add these up on your own and verify that you do indeed get the vector on the left. Now, the reason that we're discussing linear combinations is that linear systems can be written as linear combination problems. To show this, let's recall our original example from the linear systems video. And I'm going to encode this by writing it as 2 equal vectors. So let's split the vector on the right into a sum of 2 vectors, those with the x terms and those with the y terms. And look at this first vector with the x's. While x is a variable, it's also a scalar, so we can factor it out of the vector. The same is true of the second vector and y. So here, x and y are playing the role of the c sub i's, while 3, 2, and 2, -2 are the vectors. Note that the vectors are exactly the coefficients of each variable from the original linear system. Looking at just the x's, we get 3, 2, the y's give 2, -2, and these are exactly the vectors of the linear combination. Now, usually linear combinations arise in modeling of a linear problem. So let's say we're buying candy, but you can only buy it in one of the following 3 forms, and each form has a different allocation of candies. I'm going to use a table to give you the allocations. We'll label the bags as A, B, C, and each bag can have licorice, lollipops, gums, or jawbreakers. Bag A comes with 1 licorice, 3 lollipops, no gum, and 2 jawbreakers, so we indicate this in the table as so. The other 2 bags have similar but varying allocations. Now let's say we want to have exactly 100 of each candy. Let's write this as a linear combination problem, and then in turn use that to write this as a linear system. Alright, so the first thing I'm going to do is indicate how many of each bag we're going to buy. Let's use CA, CB, CC to indicate the quantities for each bag. We will use a 4x1 vector to account for which candies are purchased. Licorice is the top slot, jawbreakers is the bottom, and in this way we can encode the problem into vectors. So the total candy purchased using bag A is the number of A's that we buy times the amount of candy in bag A. Note that 1302 is exactly the candy allocation from bag A that appeared in the table above. Now we're going to do the same things for bags B and C, and we're going to add them all together. And since we want 100 of each type of candy, this must be equal to this vector of all hundreds. Thus, the corresponding linear combination problem is whether this vector of hundreds can be written as a linear combination of these 3 vectors. So to write this now as a linear system, let's expand out the linear combination problem. I'm going to take the line at the top of the screen, apply the multiplications by CA, CB, and CC, and then I'm going to add them all together. So I've combined that as a single step, but you should go through it and double check this is correct. And that must be equal to the vector of all hundreds. And now for these 2 vectors to be equal, each of their components must be equal, which gives us 4 equations in 3 unknowns. So this is a typical example of how a problem will be posed and how you will convert it into a linear system. Next up, we'll see how to write linear systems so that we can easily solve them. The way that we do this is through something called augmented matrices. Now, the key consideration is that variables of a linear system, or equivalently the scalars of a linear combination, are all implied. So all we need is some other way of bookkeeping, that is, keeping track of which coefficients go with which variable. If we write down our general linear system of m equations and n unknowns, then we can define the coefficient matrix, which is the matrix of coefficients of the linear system in the correct order. We can define the constant vector, which is unsurprisingly the vector of constant terms, and the augmented matrix, which is the coefficient matrix and the constant vector placed side by side and divided by a vertical line. This vertical line isn't strictly necessary, but it helps us keep track of where the coefficient matrix ends and the constant vector begins. So to see this in action, let's recall the linear system that we found for the candy problem we did earlier. Okay, I'm going to go straight to the augmented matrix here, because we'll see that the coefficient matrix and the constant vector appear automatically. So this 4x3 matrix here, that's the coefficient matrix, while this 4x1 vector is the constant vector. And it's worth noting that the columns of the coefficient matrix are precisely the vectors which appeared in the linear combination problem. You're going to have to scroll up to see that, but try that. And thus we have linear combinations to help us model problems, and we'll see in the next few videos how to use augmented matrices to solve these problems.